Hey class, welcome to this extra example video on deriving a reduction formula. So as you'll see in typical textbook problems, you're often just given what the reduction formula is already, and you're just asked to use integration to verify that that reduction formula actually is true, that it actually works. Now, you might wonder, well, where do the reduction formulas come from? So here we're going to take a look at an example where you kind of see this whole process of starting from scratch. How do you get a reduction formula and more or less at the same time verify that that reduction formula holds? Well, as with all reduction formulas, this is going to come via applying integration by parts. The question is exactly what are you looking for as you apply integration by parts. So here's the example we're going to take a look at. It's the derive a reduction formula for the integral of x to the n times sine of ax dx. So in any reduction formula, the idea is that you're going to have some power of something, and you're going to try to rewrite that in terms of an integral that has a lower power than the original. So that's one of the key criteria that we're looking at for a reduction formula. The other one, maybe a little more subtle, is that other than that power getting reduced, the rest of the integral should be exactly the same, more or less. So we'll actually see both of those come into play as we take a look at this example. So again, in carrying out our goal, we're certainly going to want to employ integration by parts. Sometimes there are other things involved as well, but let's see how it plays out in this example. So integration by parts, we're going to want to choose our u and our dv. So in this case, we're going to let u equal x to the n. There's a good reason for that. We're going to be differentiating u, and when we do that, the power on that x is going to get lower, which is what we're after. So that's why that is the choice to make here. And then that means that, let's see if I can get this to keep working. We also want dv to be the rest of the integrand, so that'll be sine of ax dx. By the way, here, because of the dx, we see that the variable is x. That a that's showing up in there, that is a parameter then. We consider it as a constant for purposes of integration. So for the rest of our integration by parts setup, we find the differential du, so that'll be n x to the n minus 1 dx. And then we also need to find v, and we do that by anti-differentiating sine ax dx. And remember that with that constant multiple of a on our inside here, that will translate to having a factor of 1 over a out in front of our antiderivative. We only need one antiderivative here, of course, and antiderivative of sine is negative cosine, so we'll get cosine of ax here, and then we also need that minus sign out there. So there's our v. So we'll plug this into the integration by parts formula now, and let's see if we can fit that down here. So the integral of x to the n sine ax dx is equal to, we need uv, so u is x to the n, v is negative 1 over a. Probably better put that in parentheses. That's an a, cosine ax. And then we subtract the integral of v du. V is, again, what we had just had. And then du is nx to the n minus 1 dx. Okay. Let's clean this up a little bit, see what we got. So we have negative x to the n over a cosine AX. And the minus signs are going to cancel here. We can also pull out some constants, some constant multiples, get n over a. And then the integral that we have left is integral of xn minus 1 cosine AX dx. Okay, now you say, well, great, we reduced the power on that x, the power of x that we're dealing with, and that is definitely one of the goals. And the integral looks kind of like the original, but actually it's not exactly like the original because now we've got cosine in there instead of sine. So really, this would not be considered yet final proper form for a reduction formula. So we got to keep going. We got to actually take this another step if we really want to get something that would be considered a bona fide reduction formula. So let's do it again. We got x to the n minus 1 cosine AX dx. We can reduce that power one more time, which may seem like overkill, but there's another thing that's going to do for us, and that's that it's going to get us back into something closer to the original form. So this time, we'll let u be x to the n minus 1, and dv will be cosine of ax dx. And that then will lead us to du equals n minus 1. Got to have some parentheses in there. X to the n minus 2 dx. And v, similar to what we saw before, we're going to get that 1 over a. And this time sine, no minus sign this time, sine ax. Okay, so there are our u and our dv this time. Let's put it all in here again. Maybe I better move over here to leave more space. So we got negative x to the n over a cosine ax. That part is just along for the ride. We also have this n over a, which is going to stay out here. It's going to be multiplied by everything that we get from our second application of integration by parts. And now we get uv, so x to the n minus 1. V is 1 over a sine ax. Make my a actually look like an a there, hopefully. And then minus the integral of v 1 over a sine ax. Du is n minus 1 x to the n minus 2 dx. Okay. Well, there we go. Again, we can clean this up a little bit, but you can see that we're just about home free here because now we're back to having sine in our integrand, sine ax, just like the original, and we do still have a reduced power of x. In fact, it's reduced one more than before. That's fine. That's actually great. And so we can write down our final reduction formula that we have derived. Again, we'll clean it up a little bit as we do that. X to the n sine ax dx. At the end of the day, that is equal to, we had before, negative x to the n over a times cosine ax. Okay, cleaning up, we're now going to have n over a squared x to the n minus 1 sine ax. Okay, and then finally our term with the integral is going to have minus here, and we'll have pulled out here a few things. N times n minus 1 over a squared. Because we had the a already outside here, we have another a in the denominator there. I think that's everything that we needed to pull out. And then times the integral, again, Try to make it look as much like the original as possible. X to the n minus 2. Almost the same as the original, but with a reduced power. I'll move myself out of the way here. And then times sine C sine AX, just like we had in the original, and DX, just like we had in the original as well. And so there we go. Here is our reduction formula, which we have concocted, which we have derived using integration by parts. All right. Hope you enjoyed that. We'll see you soon.